Welcome, welcome everyone. Let's start. Okay, so due to some unavoidable situation, we are not able to complete our hands-on part on 25th April. So today we will do that, cover that hands-on part. My name is Paramita Ghosh. I am a senior project engineer, CDEC Pune. So this is the outline of my talk. So first I will give brief introduction of AMDKIIT. Then I will cover overview of input and output file so that user can run their own calculation using this software. After that, we will do the hands-on. So AMDKIIT is a standalone electronic structure program. It is fully developed within the academia of our country. The source of AMDKIIT is open and freely available for everybody under MRT license. Now, to run this AMDKIIT software, we need Fortran compiler, MPI libraries, and parallel compiler. CMake version we require. CMake version 3.4 or higher we need to compile this code. To compile this code, we need 4 libraries: LAPACK, FFTW, libxc, and YML. One thing need to remember here that the version of the compiler to install this library and this AMDKIIT should be same. Otherwise, there will be an issue. First, I'll discuss the input file. 3 types of input file we need. First, coordinate file. Second one, pseudo potential file. And third one is our main input file. So first is coordinate file. This coordinate file, the geometry of the molecule has to be provided in this coordinate file in XYZ format. Okay, user can build their own XYZ file using this Gauss View, Avogadro, Molden, VMD software. So here I have given one example of water molecule. You can see here for water there is 3 atoms. So first line contain total number of atoms. Second line basically comment line. Here I have given species name. Now first column of third line. This basically represent atom indices. Okay, and second, third, and fourth column represent X, Y, and Z coordinate. And one thing you need to remember here that if you the unit of the coordinate should be mentioned in your main input file. I will discuss that part later. So this is the main coordinate file. Now the pseudo potential file. AMDKIIT software is a plane wave based electronic structure theory code with pseudo potential. To use plane wave, user need to provide the correct pseudo potential for different atoms. Currently, non-conserving pseudo potential are enabled. It has to be built for the exchange correlation functional which are being used during the calculation. Only PSP and UPF format can be used in this software. User can download pseudo potential from this pseudo dojo site. Okay, now I will show you how to download this pseudo potential file. So first, here you need to that if you want to download LDA, so you want 4.1 version. So I am selecting here 4.1 version, then exchange correlation function, then I am choosing the format. Let's choose UPF format. Suppose I want to download hydrogen. So click on hydrogen, and for oxygen, click on oxygen. Okay, see, download completed. Okay, so in this way, you can download your pseudopotential file. Now, next is our main input file. This input file should be in YML format. Okay. Now, here I will discuss in details each keyword, how to use this keyword. So, first is task. Task basically define the which type of calculation user want to run. Suppose I want to run wave function optimization. So I have mentioned here wave function optimization. If you want to run geometry optimization, then you have to mention here geometry underscore optimization. For molecular dynamics, you have to use molecular underscore dynamics. For details, user can check AMDKIIT manual, which is already given in AMDKIIT, GitHub link. Okay. Now, next, symmetry. This basically represent the symmetry of the supercell. Here I am using cubic, but user can use any symmetry like FCC, BCC, hexagonal, any symmetry user can use. Now, next part contain the supercell dimension. So here, first represent the ABC length of the supercell, and the unit of the supercell has given here. So I have expressed the dimension in angstrom, so I have mentioned unit here angstrom. Next is the angle. This is basically alpha, beta, and gamma. Okay. Now, next part contain input. This part basically this part basically contain the information regarding the coordinate file. So this is your file name, which should be in .xyz format, and this unit basically represent the unit of your coordinate. Now, the next part is species. So in this case, here I am using water. So for water, there is two type of species. So here I am using level 1 and level 2. Suppose you want to do calculation with some other molecule, there are n number of species. So you have to mention here level 1, level 2, level 3, like that. In number of level you have to use. Okay. Now, next is atom. So this basically represent the indices of the atom. PP file contain the name of the pseudopotential file. PP scheme, this is basically used to calculate the non-local pseudopotential calculation. Okay, here I am using Kleemann-Beilander scheme. If you don't want to use any scheme, so you can simply mention here none. Okay, and LMAX provides the information on the non-locality of the pseudopotential for maximum L value. Okay, now next part is the DFT part. This part is the mandatory, and one thing here need to be remembered that here I am using LDA exchange correlation. So I am using the same pseudopotential file LDA.psp. Okay. Now, next, after performing this wave function optimization, we will get two types of output file. One is main output file AMDKIIT.out, and another is sp_energy.dat. These contain basically consume energy versus time in every step. Okay. Now, for geometry optimization. For geometry optimization, as I already said, that you need to mention the task like geometry underscore optimization. And one thing is that this keyword is case sensitive. So you have to use uppercase only. Now, optimization details. Here I have mentioned optimization details. So for wave function optimization, I am using conjugate gradient. This basically specify which scheme I am using to do the optimization. Then the maximum step for the optimization, and then the gradient cutoff. So these value are given by default. If user want to their own value, they can use it here. Now, for geometry optimization, there will be three types of output. Along with AMDKIIT.out, there will be atom underscore coord.xyz. This file contain ionic coordinate per optimization step, and atom underscore force.dat. This file contain force at every optimization step. Next, molecular dynamics. So to perform molecular dynamics, you have to mention task as molecular underscore dynamics. Now for dynamics, we need some more keyword, like we need to mention temperature, maximum step, and time step. Temperature always expressed in Kelvin unit in the software. Temperature should be in Kelvin unit. And time step here is 1 femtosecond. 1 femtosecond. So these are the default value. Again, user, if user want to use their own value, they can use according to their choice. Okay. So after performing molecular dynamics, we will get three types of file: AMDKIIT.out, AMD underscore energy.dat. This file contain temperature, consumed energy, and total energy in each molecular dynamic step. And MD underscore trajectory, it contains geometry of the system at every molecular dynamics step. Now how the output file looks like. So I am showing you. This is AMDKIIT.out. Okay, so you can see here. So first this will print the version, then date and time. Then it will show the number of processors used to run this calculation. After that, it will give the information regarding the input. I mean, all the input details will be printed here. Check. Okay, so this is the input details. Now, next part is simulation parameter. Here we can check that wave function cutoff, density cutoff, simulation parameter are given here. Okay. Then the supercell information, the lattice constant, lattice type, all are mentioned here. Then the species information. Here the pseudopotential file name, coordinate, all are given. Now, this part basically represent the division of grid along the processor. See, here we are using 48 processor. So we can see the division of grid on each processor. Okay, so let's check. Okay, so see 48 processors. After that, it will print the total number of valence electron, valence orbital, then the occupation. After that, it will give optimization details. Then it will print consumed energy, energy change in each step, maximum gradient, and time in each step. So after completion of the code, you will see the details of the energy, details of the optimized energy. Check. Yeah. See here. This is the total energy, kinetic energy, electrostatic energy, all the energy in details is given. Along with that, you can see here that elapsed time and time of the completion. Okay. Now, next, how to install and compile this AMDKIIT software. So in order to install this software, you need to download an unzip file from our GitHub link. Link is given here. So first you have to unzip this folder. After that, you will see there will be a directory AMDKIIT-main, and inside that there will be a directory source. Okay. Then inside the source directory, you have to download this YML CPP library. After that, you have to install FFTW, BLAS, LAPAC, and libxc. Okay. After the installation, you can see there will be a CMake list.txt file inside the source. Okay. So AMDKIIT-main is the main directory. Inside this, there will be a directory, subdirectory source. Inside this source, you will get this CMake list.txt. So you have to open this file, and inside this file, you have to give your library path. Okay. So I am not going to cover this step here. After that, after setting library path in that text file, you have to make one directory called build. So make directory build. Then you have to type this command cd build. You have to go inside this build. Then inside this build directory, you have to type cmake space dot dot. Okay. After compilation, you have to run make command. Okay. After successfully compilation of all these steps, it will create AMDKIIT executable, AMDKIIT.x as executable. Okay. So for today's hands-on part, we have already downloaded this AMDKIIT software in our Param Brahma cluster. So to use that, you need to load this module. So this is the command to load our AMDKIIT software. Now, how to run the job? So in order to run the job, you need to mention mpi run -n, then number of processor you want to use. After that, executable name amdkit.x. After that, input.yml. This is the main input file. And after that, the output file name. Okay. Okay. So I hope till this part, everything is clear. Okay. Next, we will do the hands-on part. Okay. So for that, I am requesting all of you to logging inside this Param Brahma cluster. Login credential already given to you. Just logging and git clone using this command. Okay. I am requesting all of you to do this part. Okay. Let me stop sharing. Okay. Now I will show you how to clone and how to run. Okay. So my screen is visible. Okay. So I'm requesting all of you to first git clone using that command. Command we have shared in chat section, so you can use that. Okay. Okay. So cloning done. Let's see. See. Okay. So go inside this mscc-test input. Check. So there you can find that one directory AMDKIIT underscore input. Go inside that directory. Okay. Now here you can see various type of example are already given. So we will perform some example. So please let me know all of you able to reach till here. Please let me know if you have any issue. So today first we will do this calculation. We will perform wave function optimization of a singlet O2 molecule. Okay. So let's start. See, here we will perform wave function optimization for singlet oxygen molecule. So go to inside this directory. Okay, fine. Now let's check this input.yml. Okay. So we will perform wave function optimization. So here we have mentioned wave function underscore optimization. Now we want to do open cell calculation. So for that there is some keyword. You have to mention initialization. Under this initialization there will be an option open cell. So you want to perform open cell calculation. So you have to write here true. For closed cell, you have to mention here false. Okay. So we want to perform wave function optimization for singlet water. Okay. So for singlet water, we all know that multiplicity will be 1. Okay. So I have mentioned here multiplicity as 1. Now, other keyword I have already discussed. Just quickly check this species part. So here I am using oxygen. Oxygen contain only one type of species. So see here I have mentioned level 1. Then atom indices, oxygen. Then pseudopotential file, so pseudopotential file name, PP scheme, Lmax. After that, exchange correlation function. Okay. Hope this is clear. Now Let's check input underscore coordinate dot xyz. Okay. See, for oxygen, there will be 2 atoms. So first line contain 2. Second line basically command line. So I have mentioned here O2. Third line, first column contains species name, the atom indices. So oxygen. Then second, third, and fourth column contain X, Y, and Z. Okay, clear? Fine. Now we need pseudopotential. So you can already see here pseudopotential file is already here. So pseudopotential file here, input file is given, and we have this XYZ. Now let's check our submit file, script file to run the calculation. So here, see, we have mentioned module load cdac/mscc/amdkit to use this AMDKIIT software. Okay, fine. Then this input to IML, output name, output file name. Here we are going to use 48 processor. So I have mentioned here as 48. Okay, fine. Now let's submit. Fine. See, using this command, you can check whether job was running or not. Yeah, you can see job is running here. So this is in R state. Okay. So now check. Yeah. See, here we are getting one error file, one log file. In addition to that, our main output file and sp underscore energy dat file. Okay. Now let's check this AMDKIIT underscore O2 error. This is basically a warning. So no error is there. So you can ignore this file. Okay. And log file contain the job details. So you can see here our cluster name. Okay. Number of tasks. Fine. Now check whether job is completed or not. Yeah, our job is completed. Fine. So we will check our sp energy.file. So this file contain, this is the step, then second column contain total energy in each optimized step, and the third column contain time in each step, time required for each step. Okay. Now, I hope all of you able to follow me. Till now, if you have any query, you can ask me, because after that you have to perform one exercise. Okay. Okay. Hope all of you fine. So I have done calculation for singlet molecule, singlet oxygen molecule. Now I am requesting all of you to perform same calculation for triplet oxygen molecule. For triplet oxygen molecule. Okay. Yes. First question is symmetry information required in the input file all the time? Yes. Symmetry information is required for all time. Uh, what is column 3 in SP energy dot dat? Okay, column 3 basically represent time for each step, CPU time. Any other question? Then I am requesting all of you to perform the same calculation for triplet molecule. I hope you will be able to do this calculation. If you have any problem, you can ask me. Okay. Hope all of you able to perform the calculation for wave function optimization for triplet oxygen molecule. Should I wait or I have to do this calculation? Please let me know. Are you able to perform? Very good. Very good. Okay, fine. Okay. Let me analyze this part quickly. Okay. So you can recheck here whether you have done correctly or not. So this is our input file. So for triplet, only I have to change here. So here I have to mention 3. Okay. Then everything will remain same. Now, one more thing is that, yeah. So for this open cell calculation, usually we want to check the spin density. So here you can see I have mentioned another keyword. This for output file. Okay. So I want to print density. So I have used this keyword print underscore density as true. Okay. So it will basically give one density file, cube file. Okay. Now let's try. Okay. Fine. Okay. Getting run. Okay. Running. Fine. Okay. Now, so we have performed the calculation for triplet and singlet. So using our result, we can compare the energy of singlet state and triplet state. Can you tell me which one will be the lower energy, triplet or singlet? Please let me know. Which will be lower, for singlet state or triplet state? Any idea? Okay, let's check. Okay, we will plot this sp energy dat file for triplet molecule and as well as for singlet molecule. Okay, so yeah, see, just 1 second. Wow. See here. Yeah. So now you can see which one is lower energy. Triplet is lower than singlet. Okay. Now I'll show one more thing. So here I have already said that I have opened that option to print the density file. So you can see one cube file is here. Now I'll show you how to check this row spin cube file. Okay. Now let's check. Okay. File, new molecule, then browse, then select this row underscore spin dot cube. Okay, fine. Now you can see determine file type Gaussian cube. Now load.
Excuse me.
Yes.
It's not visible.
Okay. Let me stop sharing and share. Okay. Now it's visible.
Yes.
Okay. Thank you. Okay. So we have loaded this one. Now go to just 1 second. Representation. Create new representation. Now go to this. Just 1 second. So here you have to choose ISO surface. Just one second. Now select material, transparent, then solid surface. Yeah, apply. Okay. Now adjust your ISO value. So see, uh, uh, just one second. Hmm. See, this is our spin density plot for triplet oxygen. Okay, fine. Okay. Now let's check our second demo. Okay. Now we will perform wave function optimization for bulk water. Okay. So bulk water, here we will use 32 water. Okay. So let's see. Very easy. Thirty-two water. Okay. So wave function optimization. So first quickly check input.yml. So you can see wave function optimization I have given here. This part is almost same. Now let's check here. So here again we are using water. So species name, there will be only two types of species. So level is level 1 and level 2 only. Okay. Now we will check this input.coordinate file, how it looks like. Yeah. So this is our coordinate file for 32 water molecule. Okay. So first we have given the coordinate for oxygen, I mean species 1, then species 2. You can give in this way. Okay. Fine. So if you want to visualize this, whether it is perfect or not, you can use that also using this VMD. So using this VMD software, you can use whatever coordinate you want to use. So I'm just showing you the coordinate I am using. See, just one second. See, so this is our 32 water molecule. Okay, we will perform wave function optimization for this bulk water. Okay, submit. Okay, first let me check. Fine. Okay, I think one question is there. Just 1 second. Okay. Next question is, in which format should we download the pseudopotential file from pseudodojo? Okay, from pseudodojo, you can download UPF format. Okay. There is other version like PSP 8 and all those. So these are not compatible with AMDKIIT. You can download UPF format, or else you can download PSP, but PSP is not available in pseudodojo. You can get it from other source, Okay. Okay, fine. So I hope all of you able to perform this calculation for wave function optimization of bulk water. Now I'm requesting you to check the result of your own, whether you are able to check. If you have any issue, you can let me know. Okay, let me share. So here sp_energy.dat, you can check these files in a similar way by plotting this. Let's check the result. Yeah. Okay, fine. Okay. Now quickly move to the next exercise. Perform geometry optimization for water molecule. I am requesting all of you, please at least calculate this geometry optimization. After that, let us know the calculated OH bond length and HOH bond angle. Okay, so first I'm requesting all of you to perform geometry optimization for single water. If anyone have any issue, please let us know. And very easy calculation, perform geometry optimization for water molecule. You can use your own coordinate, no issue. And after that, check the geometry of the optimized molecule and check the bond angle and bond length. All of you able to run this geometry optimization for water molecule? Please let me know. If you have Any issue, please let us know. Okay. I hope all of you able to run. Okay, okay, running. Fine. Running. Fine, fine. Anyone else? Now, after that, you can check the output file and using VMD software, you can check the bond length and bond angle for water molecule, optimized water molecule. Okay. Yes, yes. Using VMD software, you can check. Okay. Okay. Hope all of you already performed this one. So let me show you uh, the result and let me show you how to calculate the bond length and bond angle using our output file. Okay. Okay. For water molecule, we will perform geometry optimization, right? Now, see, this is the our input file. So here we are using geometry underscore optimization. So everything is same. Now, input underscore coordinate. Okay. Quickly run this code. Okay, input file is there, pseudopotential file is there. Okay. Okay. It's running. Okay. Just 1 second. Don't. Okay. Hope it's completed. Yeah, it's completed. Now let's check the result. I think all of you already know the experimental value for this OH bond length. Now let's check our result. Hmm. Okay, so you can you can see this is the optimization step. It's moving very slowly, little bit. Okay, now stop. Okay, now we will check the bond angle and bond length for last step, that is step 8. Okay, so here you can see this is for 8. Okay, this part. So in order to check bond angle, you have to press 2, then select atom. First hydrogen, second oxygen. Hmm, Just one second. Let me select once again. Yeah. So here you can see this will show the bond length, OH bond length 9.8, sorry, 0.981798 angstrom. Okay, fine. Now we will check the bond angle. So for bond angle, you have to press 3. Then you have to select 3 atom. First hydrogen, then oxygen, then hydrogen. Okay, let me do it once again. Some issues coming, so let me off and again on. Okay, hydrogen, then select oxygen, then again. Yeah, so here you can see the angle. Okay, so this is hydrogen oxygen hydrogen bond angle 103.82.25. Okay, fine. Okay, till now if you have any issue, please let us know. all of you able to run this calculation? Please let us know. Okay, fine. If you have any query, if you want some more example, please let us know. Okay, fine. So we have completed this hands-on part. Now our question answer session. So if you have any query, please let us know. I am requesting all of you to use this software. And please give your feedback. So that we can improve our code. Okay, how can it be used to surface and crystal? Okay, uh, for surface, you have to create your own cell, super cell, I mean, own surface you have to create. So you can create that surface and use that coordinate in this input underscore. This input underscore coordinate file, and uh, that's all you can do. And as of now, k point calculation is under development, so k point calculation you can't perform. You can perform only gamma point calculation. And for specific keyword, I will request you to check the AMDKIIT manual. For cutoff, gradient cutoff, optimization, all those details. And if you have any specific query, you can post it in our forum. Okay. So thank you all. Thank you for your participation. So this is our GitHub link. You can download source code from this link. You can give your feedback here. Feedback link also shared in chat box. And this is our forum page. You can check it for new update. And this is our mailing list. If you have any query, you can reach us. Okay. Okay. Thank you, all of you. Thank you. We are going to end this session.